recommend this chapter of Shannon Lipaste, chapter 5.3 for this particular section. Hennessy Patterson also cover it, but they cover it very, very briefly. So this Shannon Lipaste is a very strongly recommended chapter for this particular topic. So if you look at Hennessy and Patterson, they give this structure for a Tomasello algorithm, which executes out of order execution. And the load store buffers are shown here. And this is a structure without the ROB. And I want you to understand why the load store buffers are connected this way to the CDP. So maybe you should think about why it is connected this way, and then also compare it with this structure wherein you have the ROB, and try and understand why the ROB is connected in a certain fashion to the memory unit here. And also remember now that there is no store buffer here because you have a ROB. So I want you to understand these two slides. Try and think about why you have store buffers here in the case without a ROB, and why the store buffers have been eliminated in the case with the ROB. So for the discussion on this load store buffers and how load stores are executed in an out of order fashion, we'll consider this structure of the machine. This is taken from Shannon Lipaste. So we assume same dispatch buffers here, the dispatch buffers, which are then connected to the reservation station here. So this is the reservation station. They have a reservation station for each of these units, and the focus for us is currently the load store unit here. So we assume there is a reservation station separately for the load store unit. So this is a different type of a model from what we have seen before. The IBM 36091 machine did not have an explicit reservation station for load stores, whereas this structure that we are discussing, so this model has an explicit reservation station for the load stores. And then you have the load store execution unit here, which is connected to the memory. You could also think of this as a cache in modern processors. And then the load stores have three steps. The first is called address generation, where you calculate the effective address. The next is address translation, which is usually only if you have a virtual memory, which we will discuss later in the course. And then the last step is the memory access step. Then the rest of the concepts are similar. You have a reorder buffer here. There is an additional store buffer here, and I will describe what is the store buffer doing here. So first let us discuss the loads. The loads have a three-step process. Like I mentioned, the first is effective address calculation. So if you have a load, you first calculate the effective address, and then if you have a virtual memory, you translate the virtual address to physical address, and then finally you perform the memory access. Of course, if you have a cache, it can speed up the memory access, and if you have a cache miss, it's going to stall the pipeline. And finally, when we do the register write back, this register write back has to happen in order through the reorder buffer. Now we'll discuss stores. Stores are a little more different, a little more complicated and a little different. The first two steps are the same. You do the effective address calculation for a store, and also do an address translation if you have a virtual memory. Now, in case of a store, we also need to read an additional register here, and this register itself might be dependent on a previous instruction. So this register content will now be read and written into the memory, and usually we do not write directly to the memory. We go through the reorder buffer, and if the store is at the head of the reorder buffer, only then you're going to write the content to the memory. This is to make sure that we do in order processing of the memory content as well. So far we have seen that in order commit only means you're writing back to the registers in order, but the other aspect is that you also want to write back to memory in order to maintain exception handling, consistent exception handling. So basically we write the register content to the ROB and not to the memory directly. This is to allow the memory being consistent and the memory is in a stable state for exception handling. And in the commit stage, it's also called retire in some books, we write to the memory. So stores write to the memory from the reorder buffer in the commit stage and not before that. And during the write to the memory, so when we are writing this store to the memory, it is possible that the data bus is busy because the load is using it. So a memory is going to have a common bus and you have reads and writes as control signals. So if the load is using this data bus, we are going to allow the load to have priority. The load is given a priority because all future instructions dependent on this load will be stalled if this load is held up. So if you do not allow this load to go ahead and perform its read from the memory, we are going to stall all future dependent instructions. Therefore, if there is a case where you want to store data to the memory, at the same time when the load is probably reading it, we allow the load to proceed and therefore the store will have to wait. And that is okay because the writing to the memory is not such a critical step right now. Because if there is any other dependent instruction on this store, you can actually directly forward the data. Therefore, the writing the store to the memory is not as critical as loading the data from memory. So therefore, what we're going to do is add this store buffer. So once we get to the head of the reorder buffer, we are going to write this the data to be stored in the memory to a store buffer. At this point, you're going to check if the data bus is free. If it is free, it can go ahead and write to the memory. So this is not on the critical path. And if the data bus is not free, it's going to wait in the store buffer till the data bus is free. So that is the role of this store buffer. So this is the structure. Okay, so let us now assume that you have a common reservation station for the load store, and we will look at how the hardware of this looks. So basically we have taken, if we go back to this previous slide, we've taken this part of the structure out and we have just shown it in an explicit manner here. So we have separated out the store and the load units just to make it clear. So store has address generation and translation. Similarly, load also has the same contents. Just that the load has an extra memory access and reading the reading of the data from the memory, whereas the store does not have that aspect. So instead, the store has written data to the store buffer, and once it is at the head of the reorder buffer, it's going to write the data to the next stage, which is called the complete stage. And then once the bus becomes free, it is going to write it to the cache or the memory. So let us now assume for some amount of this discussion that we are performing in order issue of load stores from the reservation station. So ideally we want to do this out of order, but we will first assume that it is performed in order. We also assume that there is this store buffer here. We also assume we have a cache which accesses cache which is being accessed, and stores are committed only when they are at the head of the job.